We're going to be starting the presentation now. We hope that you're all get settled in and ready for an interesting and fact-filled couple minutes with us this afternoon, or this evening, or this morning, or whatever time zone you happen to be in today. My name is Jonathan Baker. I am your presenter host for this evening. I am the head of developer relations for PingCAP, and I will be the one that kind of is just here to moderate and help you with anything. And I'll be doing all the welcome introductions and the rest of it for our presenters today. Just a brief introduction to myself. I have been doing developer relations for about 15 years now, and I've been doing technology for about 25. I'm a software engineer by trade, and I look forward to working with all kinds of new technologies and really having a lot of fun now with data storage in modern space, and also working with AI and machine learning as well. Let me do a quick introduction for you for the people that'll be speaking this evening. We have Andy Pavlo, will be our first speaker for this evening. He's an assistant professor at Carnegie Mellon, I'm gonna get that one right, out of Pittsburgh, and he is also the CEO of OtterTune. We'll be doing a presentation with him, and it'll be following up from Marshall Zhu. He's also the big data director for SHAREit this evening. So the first thing I wanted to talk to you about is why PingCAP is doing a presentation on AI for you this evening. I just wanted to spend a little bit of time explaining that entire process, and really it basically starts with an introduction on the flow of data as it pertains to AI, right? We all know that with anything, when you're doing machine learning and artificial intelligence, it's all about the information that you're gathering. And as this slide shows, that data actually usually passes through a lot of different hands on its way to whatever the model is that you're currently creating, right? We start off with something, the data source or the wellspring of the data. And usually what we find with these systems is that data source is optimized for row level transactions, for ACID transactions. Because that system was primarily designed for those transactions to be occurring on the front, those systems are usually designed and run specifically by the operations groups to be efficient for that particular purpose. And because of that, most of the data that is put through that system, that is all done in row levels in some type of a database, usually some type of relational system, then moves on from that particular system into other database and data stores. What you'll find is that there's almost always going to be multiple different data copies after that primary system exists. There'll be copies for archival purposes. There'll be copies for data reporting. There'll be copies for data streams. There'll be copies basically just to make the data easier to access and put it together. And all of those data copies go into places like data warehouses and data marts. And those will become the next source of data, or the ones that most of the data scientists will be looking at. From there, those same scientists working with AI or machine learning will try to identify the data that's actionable. So in order to make the data and find the features that they're looking for. And in order to do that, they're going to have to take that data, and they're going to be looking for a couple different pieces. They're going to be looking for actionable data. They're also going to be looking at the data syntactically and semantically to make sure that the information is consistent and can be run through the model. Obviously, right, they want to do that and provide the model with a good data set that it can work with, and that data set would be put out there in a place where the model could access it access those features in somewhat close to real time, right? But if you think about that particular data set and all the different places those data are being passed back and forth, the problem with all those data sets is that they're all copies and copies of copies and copies and copies of copies. Multiple different generations as the data is being moved from one source to another. And even with modern technology, those copies will introduce some kind of lag. So you're going to have a significant delay between the data source itself and all the different downstream copies that you're working with that particular data set. So the question then becomes, why are you doing it that way, right? Obviously, the reason most people are doing it that way is because that's the way their systems have worked for a very long time, right? They have relational data sets in one place. They want to switch to some type of reporting data set in their data warehouse or data mart. They then want to take that archival data and put it together. And because of this legacy of information storage, there's a lot of solutions have been cropped up in how to get these models the most efficient data sets and stream the most efficient data to them effectively. One of the ways, though, that we think that people should be looking at this is not just in kind of continue to tack more technology on the solutions they already have, but to take a fundamental look at the technology that they're using for data storage. One of the real problems with the data storage model is that the model itself basically relies upon there being the data being in a monolithic structure, right? It's designed to be doing one particular thing for row level transactions, right? And then they take it from there and they're working in OLTP and they want to move it over to some type of reporting or OLAP system. But what if you could put together a system that shared the commonalities of both, right? And that's what TiDB and TiKV provide. That's the system that we're actually working with. The system that PingCAP is providing actually provides the benefits of both OLTP and OLAP at the same time. That's basically known as a hybrid transactional model. And the benefit of that model is that it's first the source data is the same data you're reporting against. It doesn't have to be a warehouse. The warehouse and the data sources are the same. That solves a couple of different problems, right? One, there's no delay in downstreaming that data. And secondly, we don't require multiple mappings when the data was downstreamed and maybe denormalized into the data warehouse. You don't have to have a map for the source data at one point and a different map for the data warehouse. You can use the same map for both, right? And the TiDB and TiKV architectures are also designed for Spark, so we can have basically parallelization going on for the mapping to make it much more efficient for AI. That's why we're bringing you presentations on this stuff today, and that's why we want to talk to you more about AI and how it relates to PingCAP's products and TiDB and TiKV. Anyway, I think that's enough of a description about our products. So let's spend our next couple minutes talking to our presenters. We're going to start off with Andy Pavlo, who's going to be presenting to you. Andy, I'm going to let you take it over from here.
Awesome, thanks. All right, so let me share screen. There, you guys should be able to see that, right? I'm assuming.
Yes.
Yeah, perfect, thank you. Okay. All right, guys, let's get started. So as he said, so I'm here to talk about some OtterTune project we've been working on for a while. So this is something that we've been working on at the university at Carnegie Mellon that we have spun off in the last year as a startup. So I want to spend some time talking about the things that we've learned of taking, a sort of state-of-the-art machine learning project in the university and having it run in the real world. And what are some lessons we've learned from that process? So I'm going to begin by talking about the background information about what problem OtterTune is trying to solve and why we think machine learning is the right approach to this. And then I'll talk about how OtterTune actually works. And then I'll spend some time talking about 2 deployments we've had in the real world, and again, some things that we learned from that. And the main takeaway actually is going to be, not to disappoint anyone, is that the machine learning stuff actually is not the highest priority when you're trying to do automated database tuning. We find that all the interactions with the database system and understanding what the database system is actually trying to do turns out to be the most important part. What machine learning algorithm, what machine learning framework you end up using, less so. And then just finish up talking about what we're working on next if we have time. All right, so let's get right into this. And I think the way they're doing this is that if you have questions, post them in chat, and we can answer them at the end as follow-ups. All right, so OtterTune is focused on knob configuration tuning. So by knob, I mean a runtime parameter that the database system exposes to you, you as the human or the administrator, that allows you to control the behavior of the database system. So we call them knobs. That's sort of a catch-all phrase. MySQL calls them system variables. I think Postgres calls them settings. Right? They're all the same thing. It's something that you can set to control how the database system is going to do certain operations at runtime. So think of buffer pool sizes, caching policies, log file sizes, right? Enabling different features in the system. They all have these knobs, and they all can affect the performance of the database system quite a lot. The reason why these knobs exist is that as the developer was building the database system, at some point they had to make a decision, how much memory should I allocate for this hash table? And then rather than putting a pound define in the code and assuming that would be good enough for everyone, they instead kick the can down the road and expose it as a knob because they assume that someone else is going to come along who knows how the application wants to use the database system, knows what data you're trying to store, knows what queries you're trying to execute, and therefore will be in a better position to be able to set that knob correctly for that, for their application. Because if you can set it correctly, then you can get the best performance out of the database system. But of course, now the problem is that over the years, people have been adding, dozens and hundreds of these knobs, and the challenge of actually trying to tune these things for every individual application exceeds the sort of mental capacity of even human experts, right? And every year, new releases come out. Postgres 14 is about to come out pretty soon. they're going to have a bunch of new knobs. So just to give you an idea how bad this problem is, my PhD student did a survey where she just looked at the last 20-year release history of the two most popular open source databases, MySQL and Postgres. And every new release, she just went and counted in the documentation how many knobs they exposed. So at the beginning of the century, MySQL and Postgres each had less than 100 knobs. But then over a 20-year period, MySQL grew by 7x and Postgres grew by 5x. So again, there's a lot of knobs, and to set all these correctly is a difficult problem. Now, admittedly, for MySQL's 600 knobs, not all of them will affect performance, right? Same with Postgres. A bunch of them will be like file paths, directory names, port numbers, right? Things that you wouldn't want a machine learning algorithm or some kind of optimization tool to try to figure out how to set, because if you don't set the port number correctly, then the system doesn't work. So, but there's still enough of them, probably in the several dozen for every database system. Commercial guys have a bit more that you actually want to tune that will affect performance. So if I'm saying that the challenge of setting these knobs is super important, it can really affect the performance of your database system and its efficiency, then how are people setting these knobs today? Well, there's sort of basic 4 approaches. So one is you just DIY it, do it yourself. And typically we found when we talk to companies is that there isn't a full-time DBA anymore. It's sort of been pushed off into this, falls under this DevOps umbrella. And so that typically means is whoever set up MySQL or Postgres or whatever database using at the last job, they draw the short straw, and they're responsible for setting up the database at the new job. But they're not an expert. They're not a full-time DBA. They're just a developer. So what do they end up doing? They just Google MySQL tuning, Postgres tuning, Oracle tuning, whatever, and you're going to find a bunch of these blog articles where they recommend maybe the 5 or 6 knobs that you may want to tune to improve performance. But it's trial and error. What they're describing here oftentimes isn't the best thing to do. We have found actually in some cases where what these blogs actually recommend are actually the exact opposite that you want to do for certain applications. Right? These are sort of general good guidelines. But again, the DevOps person is just winging it. They don't really know what's going on because they don't fully understand what the database system is doing. All right, so say you don't want to DIY it. Say you want to actually be a bit more responsible, or you have a little money, you can try to hire an expert to come do this. So you can hire DBA, again, someone who is intimately familiar with the internals of the database system and maybe knows something about knob tuning. We have found actually the DBAs that we talk to that do some knob configuration tuning, they typically have, again, just maybe 5 knobs that they're comfortable with tuning that worked well for them in the past, and they try to apply that again. But the problem is this is not cheap and this is not scalable. So this is from the U.S. government, the Bureau of Labor and Statistics, from May 2019, and they have that the average salary of a DBA in the U.S. is around $96,000 a year. Again, that's the average. Certainly, if you're on the East Coast and the West Coast, DBAs are easily going to cost into the 6 figures. All right, so this is just, again, $100,000 just for one human to come, tune your database system. And DBAs are doing a bunch of other things too, right? They're doing disaster plans, they're doing query tuning, index tuning, right? Knob tuning is usually relegated to a low priority just because it's so challenging and time consuming. They have a bunch of other stuff that they need to do. So just because you hire someone for $100,000 doesn't mean they're going to come be able to tune your database immediately. And certainly if you have a fleet of hundreds, even thousands of databases, you can't hire enough humans to come and tune each database for the application that's running on it. So the next approach is to use these automated rule-based tools. So all the commercial vendors, Oracle, IBM, and SQL Server, and Microsoft, they have their own proprietary tools. There's pgtune for Postgres and MySQL Tuner for MySQL. And these all work basically the same way. They have a bunch of hard-coded heuristics written by the database developers themselves that just use, sort of conventional wisdom on how to tune things. Like for MySQL, you want to use 75% of the memory on the box for the buffer pool. Right? So they're just codifying that information. So you punch in how much CPU you have, how much memory you have, maybe what workload you're using, and then they'll spit out some basic recommendations for a small number of knobs. But we have found in the cases, when we compare against these guys, they're not optimal either, and we can beat them. So what I'm arguing for tonight or today is I think the better approach is to use machine learning, rely on the modern sort of machine learning and artificial intelligence tools that have come out in the last decade, and leverage that for tuning these configuration knobs in databases. And we think that this is going to yield to better results because you can uncover things in different implicit dependencies between these knobs that a human's not going to be able to discover. And over time, as new features get added to the database systems, it's just a matter of retraining the models with these new features and not worry about these guys ever coming and updating their code. Right? We can just learn automatically over time. So this is what OtterTune is. So OtterTune is a machine learning-based database configuration tuning service. So the idea is that we're going to train machine learning models that know how to optimize the knob configurations for different database systems in order to improve performance or improve the efficiency of the database system. And the ultimate goal is either you want to get, I want my queries to run faster, I want to run more transactions, have lower latency, or I want to actually maybe downsize my my hardware installation or my hardware specification that I'm using for my database so I can run more efficiently. Because we're all paying Jeff Bezos way too much money on AWS. So if you're over provisioning your database on Amazon, OtterTune can come and help and dial that back. So as I said in the beginning, this is a startup that we've spun out of the university. This is something we've been working on for 6 or 7 years now, and we've gone through a bunch of vetting in the academic space. And now we're actually trying to apply this, make it work in the real world, because we found that it actually did work when we used the research version. And so we're interested in seeing what happens when we try to run it at a larger scale. So there's several papers that describe the key algorithms of OtterTune that are publicly available that you can go check out. So right now, the commercial version of OtterTune supports Postgres and MySQL, all versions except for MySQL 5.5, but that's old. And then we're currently targeting Amazon, and we can either run for RDS or for Aurora. We have done deployments of OtterTune running on-prem. We haven't really been asked to run in other cloud settings like GCP or Microsoft or IBM. Right? Amazon is again, Jeff Bezos is the world's versus man for a reason, or world's versus person for a reason. A lot of the databases are running in this environment. So. It's always risky to do this while giving a live talk, but I'm going to give a demonstration of OtterTune. And so what we're going to do here is we're going to deploy Amazon, or we're going to deploy a Postgres database instance on using Amazon RDS. So RDS is their hosted database as a service, but it's the stock version of Postgres. It's not Aurora, where they've ripped out a bunch of the internals. And we're going to run the industry standard TPCC benchmark using our benchmarking framework, where we're just going to run transactions and try to measure how fast we can, we can push this system. What we're going to do is we're going to set up the database twice. We're going to have one database where we're running TPCC, but we're not going to do any tuning. We're going to call this the monitoring database, or the control database, and that's going to use the default configuration that Amazon gives you when you first set up your database. And then the second one will be one where we're going to let OtterTune actually go ahead and try to optimize configuration to improve performance. And we'll use the monitoring one as a baseline to see, are we making things better as we tune the system? So I need to replicate my screen here, which I think is going to break. Yeah, so I come back to this, share screen again. Right, I think you guys should be able to see that. All right, right, so this is the OtterTune dashboard. So we're going to go ahead and create a new database. And we're just going to plunk in a bunch of quick information. So when you run on Amazon, we're going to run Postgres. We put in our identifier. And we have to select a region. So we're on East 2. All right. Our database name, we'll call it TuningDB. We have to tell OtterTune what database we want to connect to. And then I'm not going to show this part, but we've already set up a bunch of AIM permissions in Amazon that gives OtterTune access to the database. So at this stage, what's happening is OtterTune is connecting to AWS, making sure that I actually can connect to the database and has the proper permissions to go retrieve configuration parameter groups and CloudWatch information, because we're going to use that to figure out what's happening. So at this next stage, we can specify whether we want to do tuning in the database, which actually try to optimize configuration, or just do monitoring. So because we want to actually optimize the database, we'll keep it at monitoring. And then we will there's a tuning schedule, so we ignore all that for now. But then here, OtterTune has already recommended a bunch of knobs that it wants to optimize. So we'll go ahead and let it choose the ones that it thinks is the best. So I'm not gonna talk about this here, but there's a whole separate algorithm we use to figure out what knobs we think will have the most impact on performance. And this is initially starts off based on all the global data we've collected from tuning databases. So now we're gonna go down here and put in our password information. So this is now going to allow OtterTune to connect to the database system itself. I'll talk about what permissions are actually we're using, but it's basically just to be able to go read the metrics or the internal statistics that the database system generates. I'll explain what that is as we go further along. But the key thing about OtterTune is that we actually don't need to see the queries. We don't need to see any user data, right? Because the metrics we're going to collect from the database system, pages read, pages written, so forth, that is representative enough of what the application's queries are on the database, of what you're actually trying to do in the database. So we don't need to see the queries like in Vivid Cortex. We don't need to see actually any of the user data because we're just tuning the knobs. And there's the basic information is to read whatever Postgres is generating or MySQL generates for InnoDB stats is enough for us to figure out what's going on. So now with everything sort of set up, we can go just come here. You see if OtterTune is connected to the database, it's gotten the first configuration. And we can see that we have some basic information about it. So we're gonna let this go for a bit. Let's continue with the talk, and then we'll check on it at the end and see how OtterTune compares against the baseline. So now, again, this will break if I do extend. It broke PowerPoint. Okay, so let's try that. If I got this. See all slides, and then let me share screen. Okay, I think we're back in business, right? Okay. So, all right, so how does OtterTune work? So as you saw, we have our target database that we want to tune, right? It can be an RDS, it can be on-prem, but you provide us with some basic credential information to be able to access the database system. We then store that in our, in our service, and then there's a driver running in Kubernetes that it runs in our data center or in our environment or your environment that can connect to the target database and retrieve these runtime metrics, pages read, pages written, locks held, and so forth, and the current configuration. The driver then stores that in OtterTune's internal repository where we keep track of all the databases that we've tuned before, and then we feed that into our compute engine that then trains statistical models that can predict how the database system's behavior or performance will change as we start changing the values to the knobs that we want to tune. So you tell us that we want to optimize for throughput, we want to optimize for latency, and so we'll train models to say, if I start tweaking the knobs a certain way, what happens to that objective function? And then we do a gradient descent on these models to then find a new configuration that we think will improve performance. We send that back over to the driver, who then applies it, and then we repeat the process. We just, we apply the change, wait a little bit, observe what happens, and then we come back around and see what happens. So, sorry, it's running on. It's using the timer thing. Always fun. All right, sorry. That's why it was auto transitioning. Okay, the worst default feature in PowerPoint. Okay, so I've already pointed out the one key advantage or sort of ideal characteristic of OtterTune is that the driver doesn't need to see any user data and doesn't need to see any of the queries. So there's less of a security concern, right? We're not looking at sort of the most important aspects of your business. We're only looking at these metrics. And we've done deployments in Europe, and there's security people at these major companies have looked at what we're trying to do and felt that there wasn't any GDPR violations. The other important thing aspect about this is that this feedback loop is continuous, meaning that we apply configurations that then we use them, to bolster our models to help improve the accuracy of our choices for new configurations. And at some point, the compute engine recognizes that that the models have converged for your current workload situation, that we think we have the best configuration for your database right now, and then it'll turn off tuning and to switch to a monitoring mode, and uses that to observe whether has the workload changed since we last did tuning, and if so, then it can re-enable re-enable tuning to make changes based on how the workload is shifted. So like if you put out a new release of your application, you have a bunch of queries you've never seen before that changes the workload pattern. OtterTune can recognize that and kick off the tuning process again. Okay. So I want to show two quick benchmarks we've done running on Amazon RDS. So the first one here is Postgres. We're running TPCC again. And this one here, we're gonna deploy the database, the Postgres database on 2 instance types. So the first one will be a DB M5 4x large. This is with 16 CPUs and 64 gigs of RAM. We're also gonna give it 4,000 provision IOPS. And then we're gonna have a smaller database where it has fewer CPUs and less RAM, and it has half the amount of provision IOPS. So the first main takeaway here is that, well, we're comparing against the RDS defaults. That's what Amazon gives you when you create the instance. A surprising number of people still run with the RDS default. Like they think Amazon has tuned the config for them that's going to be really good. And that's true. Amazon has tuned the configuration for the RDS deployment. It's better than like the default config you get when you do apt-get install to install Postgres on Linux or your local box. Those configs are always terrible. They assume you're running on a machine with like 160 megabytes of RAM. So Amazon has done a little bit better, but it's still terrible. PGTune is one of those rule-based tuners that I mentioned before, where you punch in your number of CPUs, the amount of RAM, and maybe what your workload type looks like, and it comes back with some basic recommendations. And then we have OtterTune is using machine learning. And so you see here that we can get over double the performance of what Amazon's going to give you by the default, in a short amount of time. And then same down here on the smaller box, we still get double the performance of what Amazon gets you by default. We still beat PGTune. But the key takeaway here for this graph is we're actually getting better performance on the smaller box than what Amazon gives you initially with the default configuration on the larger box. So this machine here will cost you $17,000 a year. This machine is half the price. So you're getting the same performance on that you're getting, you could get on this more expensive machine, but at half the cost. So this is why I'm really bullish on the idea of using machine learning. We didn't have to be an expert in Postgres to figure this out. The machine learning stuff figured it out for us. You run the same experiment now on MySQL. The machine is the same. The 2 instance types are the same, except we're now doing 2,000 provision IOPS versus 1,000 provision IOPS. And so ignore whether Postgres is faster than MySQL. Like that doesn't matter. It's really, again, that we see when we compare OtterTune against the Amazon default config. In this case here, we're getting we're getting almost getting 4x faster, and then on the smaller box, we're getting I think almost 5x faster. And so the MySQL tuner is actually a little bit more sophisticated than the PG tuner one. But the MySQL tuner actually watches the InnoDB statistics for a little bit and then makes recommendations. But in our case, because we were starting with the Amazon default config, Amazon already tweaked a bunch of the knobs that the MySQL tuner set, but we can still outperform them. And again, once again, we're getting actually better performance on the smaller, cheaper machine than you would get in the larger, more expensive machine. All right, so this machine here is going to cost you $14,000 a year, and this machine is going to cost you $7,000. So these, we ran these kind of experiments again when we were at the university. We thought this is this is amazing. This is this is definitely something that would help in the database world. We wrote our first paper in 2017 about OtterTune. We published it in SIGMOD, which is the big academic database conference. But when it came out, like nobody really paid attention to it. I mean, the other academics and the researchers saw it and like, oh, that seems like a good idea. But nobody in industry really paid attention to it. But then through total luck, I just happened to meet the guy that runs all of Amazon's machine learning division. He came to Carnegie Mellon. I got 5 minutes of his time just to thank him for giving my PhD student a couple $1,000 to run her experiments on EC2 and RDS. And he was like, great, can you write a blog article for us? because the Amazon just started a new, Amazon AI blog, and they needed articles. And so we did that. We converted our Sigma paper into a blog article for them. And when this came out, this is when everyone started emailing us and saying, we have this exact problem. We want to pay you money to fly a student out to come set up OtterTune for us. And so we got a lot of crazy emails. People talking about like, we're going to make a lot of money with this, how we're going to take over the world. This guy kept emailing me nonstop and, saying all sorts of crazy things. And so unfortunately, my PhD student didn't realize that these people were crazy and did not know, like, hey, don't respond to them, because that made things worse. But after all of this nonsense, we actually got a really interesting email from somebody in Paris who said that they were in charge of the database performance and engineering team at this major bank, and they were actually looking at using OtterTune for their giant database fleet. So this turned out to be one of the first deployments that we did of OtterTune outside the real world, because it's fun to make TPCC run faster, but we really wanted to see whether this would our approach would stand up to real world workloads. So Societe Generale is a major French bank, and they told us that they had a fleet of 1,000 Postgres databases running in their data center in Paris, and it was a self-provisioning sort of internal architecture where somebody in IT could go into a website and say, I want a new Postgres database in an online form, and then it would automatically spin up the instance for them. And so they would specify like, what the workload was going to be. And so there was some basic tuning that was being done, based on whether you select OLTP or OLAP versus HTAP. But beyond that, they had not done any sort of fine-grained tuning on each individual instance. So they told us had 1,000 Postgres databases. We collaborated with them remotely. They took on a French master student as an intern to sit on site and get OtterTune up and running inside their data center. And then once we got it working, they went to go now look at the 1,000 databases that they wanted to go tune. And then they came back to us and told us that the real number of Postgres databases that they had to tune was 1. Because what happened was the bank had this big initiative a few years prior to this, where they told everyone at the company, hey, we need to start using more open source software. So then the word got around the bank at all the managers that for every new project and the budget justification, if you just in the checkbox where you said what open source software you were going to use, you could just click Postgres. It would spin up a Postgres instance. You never put any data in it. You never ran any queries on it. You just used Oracle and paid Oracle like they normally would. And then none of the bean counters ever checked and ever cared. So they literally had 1,000 Postgres databases that were completely idle running in their data center. So this was a bust. And so then they came back to us and said, okay, yeah, we're primarily an Oracle shop. Can you port OtterTune to make it work on Oracle? And so we had a master student on our side at Carnegie Mellon port OtterTune to make it work on Oracle. And this is an important part, as I said in the beginning, it's the machine learning part doesn't change because the machine learning algorithms don't know what they're optimizing. It's just numbers. They don't know whether it's Oracle, they don't know whether it's Postgres, right? It's all the infrastructure they talked about in the driver and how that interacts with the database. That's sort of the hard part. So the student was able to get OtterTune to work on Oracle in a few months' time, but the challenge wasn't, again, making changes to the machine learning algorithms. It was making our drivers speak to Oracle, know how to work, Oracle stores configs, dealing with failures and so forth. So once we got this working, the bank gave us then access to a 1 terabyte database that had been running in production. It was a read-heavy OLTP workload. It was basically their internal version of Jira. What was interesting about it is because that the bank has like 100,000 employees all around the world. So like any time during the week, the work week, somebody's using this this internal website for ticket tracking, and so it had a lot of traffic. And this database had already been tuned by their in-house experts, and they weren't really able to make a dent in it and sort of making big changes in improving performance. So the thing they wanted us to optimize was this thing called Oracle DB time. So in my examples of TPCC, we were trying to optimize for throughput. DB time is a proprietary Oracle metric. It's basically a summation or combination of a bunch of different latencies inside the system. So again, we didn't have to make any changes to our machine learning algorithms to support this. We just had to change, tell it, hey, here's the metric we want you to optimize. So the deployment went like this. So we had our driver that was running in their data center, along with the Oracle database running in their data center. So in the very first step, what we would do is just start the database and then immediately check the logs to see whether the database came up correctly. So this turned out to be a reoccurring problem with Oracle, where if you set the knobs incorrectly, or a series of knobs incorrectly, a set of knobs incorrectly, Oracle would freak out and say, I don't want to start. And so we had to go check the logs and see whether it crashed because of something we did in the configuration or something else going wrong in the system. I should also say too, this is running on spare hardware. So they took a snapshot of a production database, captured a workload trace for 2 hours of the queries that the database was executing, and then they spun up a bunch of VMs that were running the same data center on the same hardware as the production database. And so we're running all our tests and all our experiments on replicas and not the production database. So the next step would be to clickers. Reload the database from the snapshot, and that puts the database back into the state it was in at the moment we took the snapshot after replaying the workload. So this ensures that every single time we try a new configuration, we'll always have the same starting point for the database. So we know that if we see the performance get better or worse, it's because of something we're doing in the configuration, or at least we hope it is, and not some change in the workload, because the workload is always going to be the same. And I will say that Oracle had really good tools to create snapshots and do workload replays, on the system, much better than any of the open source things I've seen for Postgres and MySQL. All right, so then the next step was we actually ran an IO micro benchmark to measure the disk read and write speed for the database system. And we had to do this because the database was running on a shared disk architecture, because for security reasons, no database was allowed to write to local storage. They always had to write to a shared NAS in the network for auditing and regulatory purposes. But the challenge was, because this was a shared disk, other things were reading and writing to it at the same time, and we'd see wild oscillations in performance. So before we ran every new configuration benchmark or every new configuration, we would run FIO and measure what the performance was on the disk. Right? So here you can see the result of this. So the red line is the measurements of running the micro benchmark on the shared disk, and then the blue line is the micro benchmark running on a local disk. You see here there's a huge blip in performance where the disk speed got 5x or 3x slower or 2x slower than what it normally should be. And this is nothing to do with what we were doing in configuration tuning with OtterTune. Just had to do with something else was going on the network. And of course, we don't know what it is because it's running in their data center. And so the challenge with this was, how do we now, how do the machine learning algorithms figure out, oh, I'm seeing a spike in my performance got worse because performance got worse for this new configuration. Is that because of something I tuned, or is it because of something happened in the environment? So we tried a bunch of tricks to try to normalize this, performance results from the database system based on what read speed we see in these micro benchmarks. And at the end of the day, it didn't actually make a difference. It just collecting more data smoothed this out and it made this go away, because most of these blips were transient. All right, so now that we're going to collect metrics from the database system, and again, these are just all the internal performance counters that every single database system maintains. And then we rerun our workload trace, and then we collect the metrics again, compute the delta between the before and after the workload. So this is like data read. You know what it is here, you know what it is after, you subtract that, and that tells you how much data you read when you're in the workload. And then we ship this over to our OtterTune service, along with the current configuration. And then we crunch on it, as we talked about before. And then OtterTune will then generate a new configuration that we send back over to the database system, to the driver, that then applies it to the database and repeat the process over and over again. So I'm going to show one graph here of the overall benefit that we were able to get for this database. And this is published in a BLDB paper we had come out this year, working with our partners at the bank, that describes the whole process of getting this deployment set up. So over here on this side of the graph, this is the configuration. Using the configuration that was tuned by their human experts. And so this is the y-axis is this DVA time, so lower is better. And then over here, you see the best configuration that OtterTune was able to generate. And so this iteration, this is how many times it sort of went around this loop, trying configuration, observing what happens, making tweaks to it, and then applying a new one. And so this is roughly a 3.5 day period. So this takes quite a bit of while because it takes a long time to reload the database and run the workload trace over and over again. So the main takeaway here is that we were able to reduce the resource consumption for this database around 50%, according to the DB time. So this is great because so now we go back to the bank and said, hey, look, we improved this database performance by 50%. How much money are you going to possibly save? And they had no idea because they were like, we've never been in a position to pay Oracle less money for our databases. So they were like, hey, this is good, but we just don't know. Back of the envelope calculation says that you probably turn off 2 CPU cores on this box. And Oracle charges, at least they say on the website, they charge about $50,000 per core. So it's roughly about $100,000 savings for this one database. But again, it's all funny money math. So take that with a grain of salt. All right, so what are some of the things we learned from this deployment? So I want to go through these quickly, and then we'll go through the next deployment. So the sort of most obvious thing here is that humans make mistakes. Human experts make mistakes. So part of the big benefit we were getting in OtterTune was because they told us that the DBAs had tuned this database, and that was sort of partially true because they had tuned it when it was an earlier version of Oracle 11. And then they did a massive upgrade across their entire fleet and bumped up to Oracle 12. And then nobody had time to go back and check, okay, should we look at these knobs again and try to retune them? And that's sort of what I'm arguing why you want an automated solution like OtterTune is because the DBAs were doing a bunch of other things, for all the databases that they had to run. They have hundreds of these giant Oracle databases, and no one had the time to look at every single one. And so my argument is that in this case here, this is a good example where an automated solution like like OtterTune could observe the database system, recognize that, oh, I've upgraded from Oracle 11, Oracle 12, or even a minor version like 12.1 to 12.2, and therefore I should reevaluate whether I'm running with the right configuration. The next challenge we had to face was actually replaying that workload. That actually turned out to be really, really hard. And the challenge is because the time it takes to replay the workload is very much dependent on what the configuration was. So it was a 2-hour trace. We took a 20-minute slice of that trace. I mean, that's what we'd run in every single iteration. But the problem is, like, sometimes if you had a bad configuration, that 20-minute trace could end up taking hours, because it was just running so slow. And so the solution to this is sort of obvious, that you just say, okay, well, if I recognize that most of the time I can finish in 20 minutes, but now it's been 2x that or 3x that, I know that I'm not going to get any useful data out of this. I know that it's a bad configuration. So let me go ahead and just kill that configuration, that trial, send some feedback information to my models and say, this is a bad configuration, don't try it again. And then that way, you're spending less time on things that end up generating useless training data for you. All right, so this works, but then now the problem is, how do we also then give feedback to the models and say things go bad? And it isn't just because things ran slower. There's other situations where the configuration was just simply, cause the system to fail to start at all. And we need feedback on our models to say, don't try this again. So I've already started to talk about the first two scenarios. The slow one, again, 20-minute trace takes an hour. You go ahead and kill it prematurely. The next one is, again, the database fails to restart, because I'm not saying OtterTune would do this because we can set the balance, but like if you set a memory size to -1, the database recognizes that that's an invalid value and then fails to start. The more challenging one that was really nuanced is when the database system fails because of a bad configuration value, but it doesn't fail right away upon boot up, it fails at some other later period. And so I don't think we've seen this in Oracle. Sorry, I don't think we've seen this in Postgres and MySQL, but we've seen this definitely in Oracle, where there is some memory buffer knob you can set, but when the system booted up, it didn't actually try to allocate that memory right away. Like for the buffer pools, every database system allocates that memory right away. But this was like for some JVM buffer or something, and the system would boot up. It's an invalid knob, but because it didn't try to allocate the memory at that moment on boot up, it boots up just fine, and you start running queries on it. Then like 5-10 minutes later, it tries to allocate the memory for that, based on that knob. Then it freaks out and says, this is an invalid value, and it goes ahead and crashes, right? So like, how do you, again, is it something because of what we did, or is it something because of the environment? Figuring that out was actually super tricky. All right, so there's two problems with bad configurations. As I said, the first one is to try to identify when there's a failure. There's no magic to this. all we do is just scrape the logs and look for well-known error messages and exit status codes and things like that. So like Postgres here, if I set the buffer pool size to a negative value, Postgres catches that when you try to boot up and throws an error. So we just scrape the log for these kind of things and recognize that, okay, something bad happened. Same thing for, in the case of like the delayed failure, there's no magic to that. You just scrape the logs and say, okay, it seg faulted or it crashed because of some knob that got set. And Oracle actually does a pretty good job telling you what the knob was. Same with MySQL and Postgres. The more tricky thing though is how to then give feedback to our machine learning models and say that this is a bad configuration and don't try it again, right? So the first idea may be, okay, I'll just set the objective value, like the throughput of latency, to like negative infinity, because that's just like, that's the worst possible number you can have, and that's enough to say, don't do that. The problem is when you start doing like gradient descent, if you have like a huge step off in your solution curve from something that was sort of okay, and then it goes down to negative affinity, then that could prevent you from maybe finding the optimal value that might be close to that cliff. And so if you look in the machine learning literature, they say just set the return value, the objective function value for a bad configuration or a bad deployment to be the worst configuration you've seen so far. And that's enough to keep the search algorithm away from trying to pick that thing again. Sometimes the literature says 2x the worst or 3x the worst. In all our deployments, we haven't seen that make a difference. So this was good. So this was, like I said, we published a paper in VLDB that proved that this worked. And this is sort of, but we still wanted to, look at more workloads and just sort of get a sense of make sure that we think OtterTune was, could be used in production environments. So the next deployment we did this year was at Booking.com. And so they actually reached out to us before the pandemic in early 2020. And, they have a large, MySQL fleet running in their data center in Amsterdam. And they want to see whether OtterTune can improve performance. They already had in-house MySQL experts that tune their database configurations. They want to see whether OtterTune can go beyond that. They had their own rule-based tuner that they wrote for their Puppet scripts. It's like whenever they deployed a new database, the script would look at what the hardware specs were, how much CPU there was, how much RAM there was, and use the conventional wisdom formulas that everyone uses to set MySQL knobs for certain things, like the buffer pool size a certain way. But beyond that, like occasionally a human would come and tune each database individually, but nobody was sort of looking at the entire fleet. So again, they reached out to us before the pandemic. Then the pandemic hit, they disappeared. Then they came back in the summer, and they were looking at using OtterTune to help them do consolidation to reduce their server footprint. So for this, OtterTune is going to end up tuning 23 knobs in MySQL. And this is going to be a combination of dynamic knobs and static knobs. And so a dynamic knob it's the MySQL term for this, but every database has these. It's the knobs you can tune without requiring you to restart the database system before they take effect. Like, you can change in the Postgres, you can change the auto vacuum settings. It doesn't require you to restart the database before the database can pick up those changes. Then there's these static knobs that do require you restart the database before they take effect. The commercial systems have fewer of these knobs that require a restart. The open source guys are getting much better, but no system can completely be modified without restarting. And so for these guys, since they wanted to optimize reduce the server footprint, increase the efficiency of MySQL running in their boxes. They want us to keep the same P99 latency for the queries, but try to reduce the number of concurrent threads and CPU utilization that MySQL is using on the node. The other thing about this too is that they didn't have a staging database or staging environment like we had at the French bank, where we could run all our experiments and not touch the production database. They wanted us to actually tune the database while it was in production. And so because of this, because I was serving live queries, it was the internal backend services for Booking.com. So it wasn't like actually serving the website; it's all the internal things. But they had real internal customers using the database actively. That we would only tune the database, 9 to 5 period during the work week when the DBA we were working with was on pager duty, and they only allowed us to restart the database once per day. In the bank's case, we could restart the database as much as we wanted because it was running on replicas that it didn't mess anything with the production database. And because this was live, we only could restart one time a day, and they want us to restart between 9 and 10 a.m. All right, so the way it worked is that we have a driver, again, running in their data center, and then we're actually going to have the driver connected to databases and collect metrics. So the first is going to be our tuning database, and this is where OtterTune is going to be actively making changes to the database's configuration. But because we don't have that workload trace we had at the French bank, we have no way of knowing whether the changes we're making are making things better or not, right? Because the workload isn't reproducible. These are read replicas. They're live queries coming in. We don't control what those queries are. So we would also connect to what we're calling the control database or monitoring database, similar to our experiment that we're showing here today, where we wouldn't do any configuration changes. We just observe what the metrics were on this system. Now, they're not running exactly the same queries because there was a load balancer in front of this where it would send query to one node. But over longer periods of time, they were essentially running the same workload because it was evenly passing the queries to each node. So we start off by collecting the metrics from both of these databases. And for this one, we would collect both a combination of InnoDB stats directly from the database system, but also a Telegraph endpoint that was collecting OS level stats on each node. So that's similar to what I'm showing here today with the SaaS version running in RDS. We can collect the CloudWatch and get additional metrics beyond what the database system is generating. All right, so then we collect our metrics, and then we just wait. Because again, we don't control the workload. We just let the application run queries on these nodes for a certain period of time. And then when the time's up, we go back and collect metrics again, compute the delta as we did before, and then ship that information over to the OtterTune service, which then generates a new configuration that we then install on the tuning database. And if it was in the time period where we were allowed to do a restart, we would go ahead and restart the system. So we actually deployed it on two databases. It worked so well on the first database, they asked us to try it on another one. And so for this first one here, the main takeaway is that we didn't really have we didn't really reduce the latency of queries that much, which is good, which is fine because that's not what they want us to do. But we were able to reduce the CPU utilization and the number of running threads in MySQL by over 20% for both of these cases. And so the back of the envelope calculation says that in a cluster with 20, 25 nodes, you're looking at maybe turn off 2 up to maybe 4 machines. So now every machine can essentially use the same hardware but do more work without affecting latency. For the second database here, we actually got a huge reduction in their P99 latency, almost 40%, but a more modest reduction in CPU utilization. This is because this particular cluster was actually underutilized quite a lot. So there wasn't enough queries being sent into it that OtterTune had enough had enough working room to actually try to improve performance. We definitely improved their latency, but not the CPU utilization level that they wanted. And that's something outside of the machine learning algorithms that we can't control. All right, so let's talk about 2 things that we learned from this deployment. The first one was actually very surprising, is that sometimes there are external factors that are involved in how people tune their databases that are not readily apparent or visible to the machine learning algorithms. And so in particular, they at Booking.com, they were setting the MySQL buffer pool size to be only 50% of the total amount of memory available to the node. So it was like each box had 128 gigs of RAM. They were only setting it to about 64 gigs. Again, the conventional wisdom of MySQL, if you read the documentation, says I think 75 to 80% of the total amount of memory on the machine should be allocated to the database system. So no surprising, OtterTune figured out that you should set it to be 96 gigs of RAM. And when we went and showed them this, we asked them why were they officially setting the memory so low, and they said because that they were concerned about flash mobs, or like an application flooding the cluster with a lot of queries all at once, and MySQL could run out of memory to try to create too many connections all at once. So they artificially set the buffer pool size low just in case at some point they have to deal with a huge flood of queries. It didn't happen that often, but it happened enough where they were concerned about it. But it was one of those things where the guy that, or whoever on their team who came up with that rule to set it to be 50% of memory that's on the box wasn't there anymore, and they didn't really, nobody really knew, whether that should still be the case in the newer versions of MySQL that they were using. So OtterTune just, doesn't know all these things, made the recommendation based purely on performance, but there are cases where you may want to set knobs a certain way, or not have OtterTune set knobs a certain way, based on sort of, other things that humans know about, but the machine learning algorithms don't. And so the way we handle this is that in the OtterTune interface, you can specify the bounds for knobs, whether certain knobs can be set correct a certain way or not. The next challenge is how to deal with the restarts. Again, in the French bank deployment on Oracle, you could restart the database anytime you wanted, no big deal, because it wouldn't affect any human or any application. But in case of this deployment, it was running in production, so we need to be more careful. The other challenge we had to deal with is, even if we could restrict when the data system was allowed to restart, how long it was going to take to restart was sort of outside our control, because it depended on many different factors of the data system, the environment, and its previous and new configuration. So the example I always like to use is MySQL has this knob that controls the log file size, and depending on what the value used to be and what you set it to, that will determine how long it's going to take before the database comes back online after a restart. So if the knob is currently set to 5 gigs, you set it to 10 gigs, restart, MySQL comes back and says, well, I was 5 gigs, now I can go up to 10 gigs. So I don't need to do anything because I'm already within my limits. But if I go from 5 gigs to 1 gig, then MySQL comes back on restart and says, well, I need to compact my log file to get down to be under my 1 gig limit. And that can take up quite a bit of time depending on how fast your disk is and what else is going on in the system. So the way we would handle restarts in the service is that this is something that a human has to tell us. We now expose in the UI the ability to say when you want to allow to restart, how many times you're allowed to restart, and OtterTune can figure out as it generates new configurations with the machine learning algorithms whether it should pick knobs that require restart if it's not within this time window when you can restart. And then if it tries a new configuration or generates a new configuration and it is in that window where it could restart, it can recognize that the knobs that it's setting don't require a restart. Like say there's some knobs that you could have tuned, but you didn't change it what it was before, and that's the only one that requires a restart. It knows that I don't have to restart, so it can apply the configuration and not just blindly bounce the system, right? Because that's trying to reduce the amount of interruption to the application from having the database offline. This sort of brings up another large point I want to bring up is there's a bunch of things that OtterTune could do to improve performance and efficiency, but we actually don't let it do these things. We actually have a deny list in the system to say don't tune certain knobs a certain way, other than just restarting. Like you can turn off fsync in your log flushes when transactions commit, and that's going to make things run really fast because you're not flushing things out to disk. And OtterTune will learn very quickly, their algorithms will learn very quickly that turning off disk writes makes things go faster, not surprisingly. But because it doesn't know, whether if the system crashes, whether your company or your organization can afford to lose the last 10 milliseconds of the log, and what are the external costs of that, it doesn't know what that is. So we actually put, tuning the knobs that way. It's something that could affect the correctness or the durability of data. We put that in the deny list. And you have to actually explicitly override it to say, okay, I'm aware of the consequences of tuning this a certain way, and let OtterTune do that for you. So we're very conservative in what OtterTune can touch, because again, certain things will improve performance, but could affect the quality of your data, the correctness of your data. All right, and then the last problem, again, we said that how long does it take to do the restart? Again, this unfortunately is ongoing research. We don't have a good answer to this. We think we're going to have to end up training another model that can predict my knobs are a certain way, and I set them to another way, and I have to restart, and then try to predict how long this can take. But it can depend on many different factors. All right, so just to finish up here, what I've shown today is that, what I've argued is that how machine learning can be used to optimize and improve the performance of databases just by tuning the knobs.
Andy, your database is now optimized and ready to use.
I always forget that. Sorry. Okay, it's on a timer. So let's go back now to to our tuning database, and I'll drag this over this here if I can. No, sorry, 1 sec. All right, let me just duplicate screen. That's just easier. Sorry, do that. Okay, so let me go back to the dashboard and refresh this. All right, so we can go to our tuning days here, and we see that we've been tuning performance, and we can go look list of our configurations. There's no way to hide this. Sorry, that doesn't matter. We can look at a list of our configurations, and we can see what OtterTune has been modifying, and we can compare against the default config that we started with. And you can see here that the changes that OtterTune has made for the knob that we want to tune. And then we go now into our performance charts. And we can see here over time how performance has changed. And you can see that, again, we start off at the very beginning doing about 1,400 transactions a second. And it looks like our peak we got was 1,800 or maybe 1,900 here. So we want to compare against our monitoring database, again, where OtterTune is collecting the data. It's not making any changes to the configuration, so we can include that in our plot. And you see here that it similarly started off around 1,200 transactions a second, and you can see how OtterTune is improving performance. So this is a short demo because this is only tuning for an hour. Could potentially let this run longer and see how OtterTune fares. But we're roughly getting around the 1,800 versus 1,500. Maybe a 10 to 20, 12, 10% to 20% improvement here. Again, if we let it longer, if we had more time, we would see OtterTune get better and better. Okay, so with that, I gotta break out of this, stop share. Let's open it up to questions. I'll share the screen again.
Thanks, Andy. We really appreciate that. It was awesome. Yeah, I'm actually kind of taking notes as we saw on the side here. Hey, we have a couple questions for you that came in the chat. We're going to start with a couple of these. Let's start off with this one. How do you ensure the robustness of the configuration that you recommended? I mean, are there any ways to you did a little bit talk about this? I think I just want to make sure that are there any ways to guarantee that robustness to make sure that the system doesn't break down? You discussed that a little briefly. Do you want to just cover that again really quick?
So can they define what they mean by robustness? Like the quality of the configuration?
Well, I would say that that's the question we got, but I will take a look and see whether they can come back and ask for some more. So we'll wait for them to come back with some more.
So just repeat the question. So the question is, how can we guarantee the robustness of the configurations?
Yes.
In some ways, you can't, right? Because it's machine learning. It's how to say this? There's no guarantee that during the sort of discovery phase of when it's trying out, when it has no prior knowledge, you can't guarantee that, like, oh, I'm immediately going to jump to the magical best solution. Because if that was the case, then you didn't need any of this machine learning stuff. So I think the way we're proceeding with this is that as we get more people using the OtterTune service, we see more databases, we see more different workloads, and that we use that to bolster our models so that in the future, when someone comes along with a database we've never seen before, but it looks very similar to a database we tuned the prior week, then it would take less time for us to generate a better configuration. All right, maybe that gets us the 80% of the benefit of what OtterTune could get right away. And then over time, as we sort of hone the models or customize it for exactly what your application is trying to do, then we can get even better performance. So there's other guardrails that I talked about to make sure that OtterTune doesn't try random things that would put you in a bad state. Like, for example, the buffer pool size. MySQL, Postgres, every database system will let you set it to really small values. Like, you could set it to 10 megabytes. But we know as humans that that's stupid. That's not something we want to do. So when we do our sampling process, we're looking at deciles or quantiles of potential values where we know that it's in the right direction. Right. So an obvious thing is like when you first time you look at an RDS instance, if you're running with a default RDS configuration, you probably don't want to reduce the buffer pool size, right? You want to at least use that as the starting point and figure out how high you actually should put it.
Yep. I think, yep, that makes sense. And yep, thanks for answering that one. So the next question that came in was, are there any support right now for non-relational databases in your model? Do you do any knob tuning for any non-relationals?
So we get this question a lot. We've been asked mostly for Cassandra of all the NoSQL non-relational databases. Again, there's nothing in our machine learning algorithms that are specific to Postgres, MySQL, Oracle, or whatever database. It's all, again, the driver infrastructure. So, my background is in Postgres and MySQL. My PhD advisor embedded Postgres. I'm focused on that, and I think there's a larger install base for those systems. If someone's very interested in using OtterTune for a NoSQL system, by all means, let us know. Reach out to us, and we can see what we can do. But we just have not seen the demand for other, at the same level of Postgres and MySQL for other database systems.
Sure.
SQL Server is probably the next database we would probably choose. I can't guarantee that, but that's most of our, for the requests of the databases we don't currently support, SQL Server comes up next.
And thanks for that answer. And the next one that came in was, and I think this is something that maybe you could clarify again, was how does the initial configuration affect the tuning performance? Does your system provide a way to basically get out of a bad local initial configuration to basically get to a better tuning, or is it just a continuous process of optimization?
So the question is, if I have a really bad configuration, is that going to hamper me from getting to a much better configuration? Like if I'm at a really bad state, is that going to prevent me from getting to where I should be? No, it could potentially mean it could take longer. It depends. There's other factors involved in it. Like if your workload is very random, it's the number of queries you're executing during the day just varies all the time. That can take a long time to figure out what's going on. If you have like a binaural pattern where there's more queries during the day, less queries at night, and that's very cyclic, we can constrain the tuning window to look at that period. I haven't seen the case. Yeah, it's a good question. I don't think it should be a problem. We haven't seen one where somebody has like a terrible configuration. I mean, we've done deployments where we start off with the default Ubuntu configuration, and what happens is in the very beginning, if you don't have any training data, you do the sampling period for the first 10 iterations. It's called Latin hypercube sampling. It's not a technique we invented. It's a standard approach in machine learning. But that's where you're looking at random values in different sort of bucket ranges, and that'll allow you to break out of that terrible configuration pretty quickly.
Okay, great. So the next question comes around about something called the Autonomous Database by Oracle. Have you heard about it? Yeah.
Every time we get asked this every time. Yes.
You got it. Okay, great.
Yes. Do you want me to just pontificate about it? Is that question, or
I think they were just asking for pros and cons and versus that. Great. So
okay. So yeah. I know that people working on the Oracle's autonomous database stuff, I think very highly of them. They're taking a sort of somewhat a white box approach, like they're modifying the internals of the database system to introduce some of their tuning tuning capabilities. Some of it has been enhanced, but a lot of it is actually running the same sort of methods and algorithms that they developed in the 2000s, sort of with these sort of GUI tools or local tools that DBAs would run that would make recommendations, to make changes. So a lot of that still is based on that sort of prior technology. They've enhanced a bunch of it with machine learning, reinforcement learning, which I think is good. Oracle's thing is doing a lot more, right? They're doing index tuning, they're doing partitioning, they're doing security patches, they're doing a whole bunch of things. OtterTune is currently only focused on knob tuning because we think that's and we can work in other database systems, whereas Oracle's only going to work at Oracle. Right. Oracle also has their MySQL HeatWave. They just announced their autopilot feature a few weeks ago. That is not doing knob tuning, and the tuning components that they provide, they're all recommendation tools, meaning they don't actually apply the changes automatically. A human has to come and say yes, 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 and click yes, and make things happen. Microsoft has a bunch of the stuff in the space. They were at the forefront of automated database tuning in the 2000s with the Auto Admin project. Some of that stuff is showing up in SQL Server Azure, so they can do index tuning. All that stuff I think is great. There isn't going to be anybody trying to make an autonomous version of Postgres, at least not in the short term, right? It's just too many moving parts.
Right, that makes sense. So, and the next question actually is a really interesting one. About in real time, can you integrate OtterTune with a database optimizer so that it could change the configurations in real time for workload changes?
So the question, like the optimizer for query planning.
Yeah, I think that's what they're looking for is query planning, because they're looking for. I think they're asking if you can, like how you would work in kind of a real time workload if there were suddenly major changes in workload or shifts in workload. Would OtterTune be able to catch those and help optimize for that as well?
Yeah. So we don't have anything public about this. We've been working on doing workload shift detection, and we actually think we can use sort of the same models that we have to do prediction of like how much better we think the system will be based on a new configuration. You can sort of use the same models to recognize that, hey, we thought we were running with the best configuration because the workload used to look like this, but now something has changed, something has shifted, and therefore we should retune things. That currently does not exist in the commercial version. Yeah, so it could be done for this. For stuff with the query optimizer actually isn't going to make a difference. There are some knobs you can tune that would, at least in Postgres, you can change the cost estimations or ratios of cost estimates for sequential scans versus index scans, and tweaking those can actually help. But to do this in real time, you wouldn't actually use the optimizer. You basically want to use the same infrastructure we have now, where we're observing the workload, we're observing these metrics, and use that to trigger. Then, hey, something has changed. Let me go ahead and apply new configuration. Then, what we want to be able to do, what we currently can't do, is provide a human explainable or human explanation or human readable explanation of why things have changed or why your workload did a certain thing or why we tune these things a certain way. Like we want to be able to do is like, if we detect one of these workload shifts and say, hey, yesterday your workload was very read heavy, but now it looks like it's more write heavy. That's why OtterTune changed these knobs. I think that's what people would want, and we're just not there yet. But this is something we're interested in doing.
Okay, I think we have time for one more question, so I'm going to pull one off the end of the list. One of the persons has asked if you can give a little bit more differentiation on the difference between your configuration changes and potential environmental changes. Right? Does your system detect environmental changes, and if so, how does that work? But I mean, they're just wondering like if you can clear up the difference between the two.
Yeah. So this is so they're basically asking like if my hardware changes a certain way, like the disk gets slower because of degradation problems. If I'm running in a VM and there's somebody else is in a VM on the same box as me and they're like doing Bitcoin mining and it slows me down, how do I handle that? This is part of the reason why we're focusing on RDS, because that at least gives us a stable environment in terms of like, it gives us an environment where the hardware is standardized, meaning we don't have to worry about sort of arbitrary SSDs or off-brand RAM people are using, right? If you're running on-prem. And so we're not there yet. We think we can use, again, the same models to sort of recognize that, you're on a box that has, this instance size, this amount of provision apps, you should be getting roughly this performance, but we identify that you're not getting that. And so we could, maybe alert you to say, hey, you're not getting the best performance in the current instance size you're at. Maybe you want to transition to something else. It's sort of related to capacity planning. Can I figure out like what performance I should be getting or would I be getting if I downsize or upgrade? So this is a very, very hard problem. We don't have an answer to it just yet. I think that the next step, actually, I will say, RDS is actually pretty good in terms of like, you seem to be isolated from your neighbors. We have not seen sort of wild swings in performance. I know people have reported like 20% differences, but so far we haven't really seen it. Yeah, I'm sure it happens, but I just don't know yet. But I think the first problem we're trying to solve is actually capacity planning. To use our same models to say, you're running on this instance size, this amount of provision IOPS, you're paying Amazon this much. If you downgrade or upgrade or tweak your provision IOPS, you'll get this performance, and then we can guide them to see whether they want to make that change. I think that's sort of the first approach that we can do, assuming that the Harvard environment is stable. And then once we have that working, we can then use that as like a watchdog to see whether things have changed enough, or you're not getting the performance you should be getting.
Okay. Well, thanks so much, Andy. We appreciate all your time talking to us about this. It's been great having you, and we really that was a great presentation. Thanks
Awesome.
again.
Thanks for the question. See you guys.
Yep. And everyone, the next person that'll be presenting to us as we're releasing this and moving on to is we'll be going on to Marshall Zhu. And so, Marshall, if you'd like to step in and introduce yourself and take over the screen sharing, we're ready for you to begin.
Okay, all right. Thanks, Jonathan.
Sure.
Okay. Hi, everyone. After Andy's presentation, I'm very glad here to share our thinking about AI platform. As you all know, machine learning has become a toolkit that is easy to reach out for every startup company. But what makes AI powerful is not a typical model. It relies on efficient iterations in the AI workflow, including preparation, build, and deployment. Meanwhile, the recommendation system acts as one of the most important AI scenarios. So it's inevitable to deal with many handshakes with the platform. So today's talk, we will be talking about AI platform and the recommendation system implementation in SHAREit. We will talk about this AI workflow and how we fix it. Okay, here is an introduction. An introduction about SHAREit group. SHAREit group is dedicated to building high quality content platforms that it connects users and content globally. Our diversified suite of applications, including our core app SHAREit, have been installed by nearly 2.4 billion users worldwide. The business network has reached up 150 countries and regions in 45 different languages. And SHAREit was recently ranked as the second top Southeast Asia headquartered applications publisher worldwide for 2020 by App Annie. So in short, SHAREit is an app that delivers all kinds of content, pictures, videos, and apps. We serve users globally, and we have hundreds of millions of monthly active users and diverse big data scenarios. Oh, this is a picture of younger me. My name is Marshall, and I'm located in Beijing. I'm the big data director of SHAREit. From a technical view, I focus on data and AI, and I have worked on it for nearly 7 years. I have two interests. One is data and AI democratization. The other is multi-cloud hybrid architecture. From a business view, I'm familiar with user groups and advertising. There are three groups of my team. First one is data infrastructure, including compute and storage. The second one is data platform and production. They engage to democratize data and AI. The last one is data warehouse. They facing data pipeline requirements, and they support data analysts, data scientists, and algorithm engineer or machine learning engineers. Oh, sorry. I found there is some time latency during the Zoom meeting, so maybe I will stay for a few seconds between the pages. Okay, this is today's agenda. When we talk about database powers AI, what we are looking for is the entry point. This talk takes AI workflow as the insurance and introduce the whole topic from the demand, conception, implementation to application. Corresponding to these 4 steps, a more practical description is about demand is equal to what hurts the most. The next is conception. Conception comes from our convolving and the understanding of the current situation. Implementation. I will describe a locally adapted AI platform, especially focusing on feature store architecture. As for application, I will take the communication between the recommendation system and AI platform as an example, and our thinking and practice on TiKV and TiDB. Okay, let's start from demand. Conception and implementation came from the current pain points. Through researching actual frontline colleagues, we found that the biggest pain point now is that algorithm engineer or machine learning engineer spends too much time doing non-algorithm work, which makes algorithm engineers less AI. Let's look at the table named time consumption. First of all, the time consumption is roughly divided into 3 parts. The data preparation. The data preparation takes up 50% of the algorithm engineer's time. And this process not only involves itself, but also involves the data engineer. The second one is model training and strategy development. This work are their own job, but due to the current weak standardization, it also involves interaction with system engineers. Finally, the deployment. Although the time not too much, it must rely on the scheduling of the system engineer. So the slow pace leads to lower efficiency and higher risk. Based on their descriptions, we have found and we have obtained several information. The first one is that a rough split of AI workflow, and the second is there are 3 roles: data engineers, server system engineers, and the algorithm engineer itself. And I draw some pictures next to the table. You can see these 3 roles. Starting from this page, our introduction will focus on this workflow, this AI workflow, and these 3 roles. Okay, let's look at the flow chart below. No, everyone is unhappy in every step. The main reason comes from these problems. For many startups, AI is within reach, but the data platform and the metadata governance are often incomplete. Therefore, algorithm engineers often ask the above questions, such as where is data source, how to extract features, how to build a pipeline. Therefore, algorithm engineer and finally they have no choice. Finally they have no choice but to ask help from data engineer. It is difficult to avoid using GPU resources for model training, but distributed GPU training is not available out of the box. So the assistance of a system engineer's colleagues is very required. In addition, algorithm engineers often use Python, and the recommendation system is written in C++ or Go. Logical translation is really a headache. The next section, deployment. Deployment as an algorithm engineer, they can do nothing but wait. I believe that this difficult position is an inevitable stage for most companies, and how to make this stage more smooth and short. So we had to deep into. Let's move to the next page. Okay, there is a conception. A conception is equal to our understanding of current situation. So when we refine the rough steps we talked about, we found that the current workflow is inevitable serial, but the main problem is that the efficiency of each step is very low. Let's pay attention to the flow chart. The process is from left to right. Okay, it is still the AI workflow, and we divide each step into several detailed processes. We use colors to identify the roles required in every process. Now you can see After zooming, almost all processes need more than one row, and too many dependencies lead to endless communication. Every R&D friend should have the same experience. Dependencies and communications often bring efficiency problems. Every R&D friend maybe want to coding quiet. Let me introduce the noun and our definition first. Operators rejection and features rejection. Features as the attributes or properties modules used during training and inference to make predictions. For example, when recommend a video list, features including video categories, user age are very useful. The generation of the feature includes the selection of the original fields, the operator, and the target feature name. Our operator rejection is equal to writing a unified method. And the feature rejection is to combine original fields, the operator, to complete a feature. The operator rejection is currently being developed by the system engineer because it is written by C++. And it's also our own problem, our typical own problem. And the feature rejection is a data engineer because it involves the complex modification of ETL codes. The sample generation process. The sample generation process is sampling is very important and common in every machine learning working flow. So this process is currently being developed by the system engineer because it is the sample. The sample generation process requires frequent communication, and the data engineer and the algorithm engineer will work together to accomplish. And the model training strategy development, the strategy development and the deployment are all the same. And there are three service goals here: feature extraction, inference, and monitor. You can find that the entire workflow is conforms to the AI paradigm of AI regulation. However, the core time-consuming steps are caused by insufficient standards and frequent interactions. Therefore, we divide every step into many processes and to solve each problem separately. Okay, let's move to the solution implementation. In the stage of rapid business development and explosive needs, it is very important for us to win long-term and short-term goals. So we build the platform on a broad set of capabilities that we already have. During this period, we have two principles. First one is build production lines through integration. The production line is very important for efficiency. The second is divide and conquer. First, build production lines to elaborate the labor force that currently supports business requirements, and then focus more on the improvement of each module. Of course, we also learned about some commercial products in the industry, such as AWS SageMaker. I believe everyone heard about it, and Databricks has its own product. Yeah, before launching our own AI platform, we have tried many times, but SageMaker bases on a series of standards, and we just use some modules. And there are still some specific requirements that it didn't support. So it is very difficult to do some migration from our system to the SageMaker system. I think it is a common issue for every startup companies. So we designed our own solution. We have 4 modules. Let's look at the picture. We have four modules. And these modules cover all the machine learning workspace. After this modules, I believe every machine learning engineer will happier. Yeah. First one is feature store. Feature store solving data preparation problems. It composed of online storage and offline storage. Later we will discuss it deeply. The second one is training pipeline. Training pipeline provides templates for training and strategy development. And this kind of template is mainly composed of some Python modules. Serving framework, the interaction with the application side. And the most important application is the recommendation system. The last, deployment and test. Deployment and A/B test are natural important processes for all iterations, not only in machine learning. These modules bring us 4 advantages. Firstly, feature sharing, feature meta information sharing, and we will reuse feature pipeline to reduce the compute cost. It is very important, especially on these days we all use cloud. Secondly, sample pool management. It can diversify the use of data, speed up calculations, and optimize costs. Thirdly, model training, model management, automatic resource allocation, and improved model training efficiency. The last is deployment. And there are still this service, feature extraction, inference, and monitor. Okay. Let's deep into the feature store architecture. It is very clear to see feature store is composed of 2 links. The first one is the online streaming link. The online storage, the low latency, high availability cache for features group that enables real-time lookup of records. It is usually used for serving online service. We collect client logs and server logs to Kafka topics. Then we use Flink to accomplish streaming computation, output raw fields and indicators, and write it to online storage, serving the real-time inference. In other words, the real-time inference is the recommendation service. We currently use self-developed KV for online storage, named SHAREit, and we will gradually switch to TiKV. As the flow chart shows, write and read QPS is very high, and the demand is very strict. The second is offline data stream, offline storage. Offline storage stores lots of historical data. It is used when offline feature exploration, model training, and batch inference. Sorry, wait a second. Okay, let's restart with offline storage. Raw data sync to data lake from Kafka. Then we use Spark to generate raw indicators table through hourly and daily merge. The raw indicators table is very important. Next, after feature extraction, a feature table is generated based on the raw indicator table and the feature table. Algorithm engineers will generate their own sample for offline training, and these samples belonging to the sample pool. We supply the sample pool management. Throughout the pipeline, we are advancing modularized SQL to describe business logic, and at the same time implement version control through the slot mode and the data lake technology, such as Iceberg or Hoodie. After talking about online and offline storage, let's move to the online and the offline scoop. We use the same Git repository to write the feature extraction code, generate a C++ shared object file and the configuration file. All feature extractions will use this package to solve the online and offline scoop. Okay, let's talk about the application. After talking about the main feature store architecture, let's think about the application. Needless to say, the main scenario is recommendation. Regarding the recommendation architecture, its paradigm is very mature, from recall, cost ranking, re-ranking to mechanism turning. Here we will focus more on the intersection of feature store and the recommendation system. This is also where we face more challenges. and how TiKV and DB help us. In SHAREit, we have two scenarios involving recommendation. One is the content side, and the other is the advertising side. We use a general recommendation architecture to support all these scenarios, including model server to complete the recommendation workflow, and the prediction server to complete the CTR or eCPM estimation. In content scenario, we pay more attention to the timeless of user behaviors feedback. Client events are returned with a delay with some time latency. So we have a strong demand for streaming compute. In the advertising scenario, because of the huge amount of traffic, one request will involve a large amount of feature readings. So these scenarios are very strict for our KV or DB selection. Initially, we thought of Flink and general KV. For example, a new user uses the feeds flow, and we hope to recommend the new contents based on the operations on the first screen within 5 to 10 seconds. At the same time, we also think about DB, because the SQL interface provided by DB not only can improve the efficiency of development and maintenance, but also lay a solid foundation for standardization and automation. These are two parts that's how TiKV and TiDB help us. Firstly, the online storage interactions with recommendation system. Some number of status is on the picture. Online storage is a usual way to use KV. And the secondly is what we are planning now, or we are doing now. Online learning. Online learning is very popular nowadays. So we plan to try some online learning. See whether it is have lots of benefits. So online learning there shows a simple flow chart. Online machine learning is a method of machine learning in which data becomes available in a sequential order and is used to update the best predictor for future data at each step. Simply saying, using incremental data which containing user impressions and clicks to enhance the older model. So we tend to call it combined storage, belonging to feature store. We tend to call it combined storage, because if the data merge and the feature extraction mentioned earlier can be finished in the streaming way, based on the adjustment of the window, we can combine the streaming and the offline computation processes into one, and sync data to the lake through hourly scheduling. Therefore, it is not only online storage, but also solve the complex offline logic problems. So why we use TiKV or TiDB? First of all, in the online storage scenario, we had a self-developed KV we talk about, and we invested a lot of human resources to this self-developed KV. We plan not to build wheels at the bottom, but use the power of the community. As for online learning, we hope that the storage can support high concurrency streaming rates. At the same time, on the read side, it involves a lot of business logical descriptions. And we hope to lay the foundation for future automation as much as possible. So it would be better if there is a SQL interface. If not, the logical description in Flink will inevitably become complicated. So our online learning hopes to train the sample in 5 to 10 minutes, in every 5 to 10 minutes. According to the amount of data latency can be trade off. So after the test, TiDB is considered a reliable choice. Okay, let's move to the next page. Stand on TiKV's shoulder. When we first investigated, we found that TiKV as a general KV story is something we need. We decided to embrace open source. At the same time, we also hope to abstract some of our internal experience and contribute to the community. So we stand on TiKV's shoulder. there are two main work. The first thing is to support multiple types at the proxy layer. You can see on the picture. For example, set, this set, hash, and the counter. This is actually a recommended requirement. In addition, as a storage role, KV interacts closely with the big data ecology. And in these scenarios, they often require batch input and batch export of data. Through this realization, we integrate TiKV or TiDB into the data and AI pipeline. Afterwards, users do not need to worry about storage choices. These two works we are doing now. Okay. All right, that's all for today. In summary, how DB powers AI. Let's look at the table. So there are some data disclosure in these two parts. We talk about online storage and online learning. The storage level is TB and QPS is higher than 50 seconds. And on online learning, each window is 5 minutes. And after what we have done, the 50% cost decreased to 25 or less during the workflow, during the AI workflow, which make algorithm engineers happier a lot. Today, when the big data paradigm is clear, users are often affected by the empirical thinking of the scenario. However, we divided the scenario into several demand points first. According to the different quantity needs, discuss and combine our new solution. The usage of DB bring us some new angle. Single link latency is very important, but if interface can lay the foundation for subsequent modularization and automation, it will be more beneficial to the iterations. So we choose DB to support our online learning scenario. Meanwhile, in the stage of rapid business development, we divided and gradually delivered the big plan, which also won more resources for our long-term tasks. Okay, I hope to be useful for everyone. Thank you. That's all for today.
Thank you, Marshall. That was actually a really excellent presentation. We really appreciate it. We do have a couple of questions that came in for you. Do you mind answering a few questions before we finish?
Mm-hmm.
Okay, great. So listen, the first one was, can you tell us a little bit about the advantages of TiKV as compared to say like Redis or Redis persistent cache or the Redis cluster?
Okay, all right. In online recommendation scenario, okay, I chose online recommendation scenario to explain this, to answer this question. Sure. In online recommendation scenario, a request often involves a large number of feature queries. And some features are also of large value type. So Redis is not work in every time. First of all, TiKV, a general purpose KV, it provides us with stable performance compared to Redis cluster, and it is easier to integration and interaction with the big data ecosystem. The last and most important thing is cost, which is a very significant cost down action using TiKV to replace Redis.
Mm-hmm. Okay, great. And my second question is, so why are you using TiKV instead of TiDB? I mean, you mentioned both at some points in your presentation, but you focused on TiKV. Why did you choose that one?
Mm-hmm. We have talked a lot about this using TiKV or TiDB. Still in the recommendation scenario, yeah, we have high requirements for latency, and the complex logic is generally implemented on the server side. Therefore, we hope that online storage is a simpler KV, and the added benefits provided by DB cannot be highlighted in the online storage scenario. But on the other side, in the online machine learning scenario, the DB's SQL interface is very worth to try. So we choose TiKV or TiDB in different scenarios.
Well, thank you very much, Marshall. We appreciate your presentation. That was really great. And thanks for all your time.
All right, thank you.
Yep. Thank you. Mm-hmm. So So just wanted to finish off today with just a quick overview. So again, you can, along with these two presenters' information, you can learn more about us by joining our Slack community at TiDB community at slack.com. You can also learn more about PingCAP at PingCAP, and we will be talking more with about these presenters. We've actually already answered a few questions on our Slack community as well. Just a quick note, by the way, we are a global organization. We have operating currently in 9 countries around the world. We currently have headquarters in San Mateo, and we are in a process right now of hiring. We're basically doing major expansion, and we're looking for people in the business space, community and marketing, in our technical product areas, and in our corporate functions as well. So if you're interested in looking, take a look at our PingCAP website for our jobs and positions. Anyway, thank you very much for attending our presentation today. It's been a pleasure to have you all. Have a good day, afternoon, evening. Bye-bye.